let's dive right into today's explainer, because we are conducting a full-blown forensic audit of a massive bureaucratic standoff. We're stepping into the highly technical and honestly quite controversial world of Japanese grid cybersecurity. Specifically, we're dissecting MIT's official reply to IS3's 8 public questions about the JC Star regulation. We're going to methodically unpack the logical paradoxes buried in this framework. We'll look at how it treats different energy sources completely differently, its frankly baffling view of network security, and most importantly, how it seemingly contradicts the absolute, indisputable laws of electrical physics.
To set the stage, let's look at this core premise from IS3's analysis. They state, large centralized systems that assume they are safe become the most dangerous. It's a brilliant piece of Socratic irony, right? You have to ask, does forcing a massive, diverse energy grid into a single, homogeneous, certified standard actually protect it? Or does creating a sprawling network where every single device shares the exact same static paperwork just inadvertently create a giant, systemic, single point of failure for hackers to exploit all at once? So here's our roadmap for this investigation. We'll start with the secret review paradox, then move into the glaring solar versus wind mismatch, tackle the static certification fallacy, look at how the policy is denying the laws of physics, and finally, present the LEAA alternative. Okay, let's jump right into part 1, the secret review paradox, which exposes a massive bureaucratic double standard. The whole foundation of the JC Star Level 1 certification is officially designated as a self-declaration of conformity, or SDOC. Now, under standard international administrative law, think of the FCC in the US or the CE marking in Europe, a self-declaration means exactly what it sounds like. The criteria are completely public, you declare that you meet them, and acceptance is mechanically determined against those specific criteria. If you lie, well, you get caught in post-market surveillance. It's a system that's fundamentally predictable, transparent, and accountable.
But then, you read the official guideline from the IPA, that's the agency actually running the system, it literally says, applications are not necessarily accepted. Applications may be rejected as a result of the verification process due to nonconformity with the requirements. Wait, what? The bureaucratic double standard here is just staggering. If this is genuinely a self-declaration, how in the world is there a non-public, pre-acceptance verification process where you can simply be rejected?
IS3 points out that METI and the IPA don't disclose the application statistics, and they definitely don't disclose the detailed criteria for rejection. So, it begs the question, how exactly can a self-declaration have a secret failure state with completely undisclosed criteria? It exists in this incredibly paradoxical middle ground where it claims the efficiency of a self-declaration, but operates with the total opacity of a closed-door screening process. Which brings us to our second exhibit, the solar versus wind mismatch, where the policy seemingly ignores standard trust boundaries.
This is where the technical analysis gets incredibly sharp. Think about it. Both wind and solar are distributed energy resources connected to the internet. The cyber attack path, meaning the jump from the open internet into the internal network, is exactly the same for both. Yet, the policy treats them completely differently. For wind power, the regulation logically mandates securing the boundary using gateways and firewalls. Makes sense, right? But for solar, the regulation flips entirely. It inexplicably mandates securing the end devices, like the inverters and energy management systems buried deep inside the network.
The reality on paper is glaring. Starting in April 2027, the official grid code actually mandates that solar PV facilities use JC Star's certified end products. They are literally forced to secure the endpoints. This completely ignores international cybersecurity standards like IEC 62443, which loudly and clearly preach a boundary-first, zone and conduit approach to network defense.
But for wind power, totally different story. Wind is explicitly allowed to use that boundary-only approach. Just put a firewall at the gateway and you're good. Why the difference? Well, as the study group minutes admit, wind turbines have over 100 internal IP devices, mostly foreign-made, and forcing Japanese-specific certifications on them would completely wreck the supply chain. So the logically sound internationally recognized boundary defense used for wind wasn't chosen because of a coherent risk assessment. Nope, it was a compromise born from supply chain convenience, while solar gets stuck with an endpoint mandate that completely defies standard network architecture.
All right, let's look at part 3, the static certification fallacy and the reality of 20 years of network drift.
Think about the lifespan of a power plant. They operate for 20 years. Over 2 decades, the sheer volume of network configuration drift is absolutely massive.
I mean, you're going to swap out your LTE routers 3 to 6 times, right? You'll replace loggers, you'll change cloud monitoring providers, and you'll definitely push multiple over-the-air firmware updates. Yet, incredibly, none of these massive, fundamental changes to the network parameter invalidate the initial, static product certification of the solar inverter. The entire network changes around it, but the paperwork says everything is exactly the same.
The pure logic here really speaks for itself. IS3 argues, and quite effectively, that a one-time static product certification is fundamentally incapable of securing a continuously drifting, dynamic network. A static sticker on a device simply does not protect the constantly shifting network perimeter around it.
Let's move to Section 4, Denying the Laws of Physics and the Load Equivalence Gap.
Now we're dropping the IT critique and shifting gears entirely to the absolute, undeniable laws of electrical physics. The crucial concept here is load equivalence. You see, many solar installations are built purely for self-consumption. They use a physical hardware component called a reverse power flow relay, or RPR. This physically blocks any power from flowing back into the wider grid. Because of this hard physical limitation, the facility acts purely as a general consumer of electricity. It's just a load. Under the laws of physics, it is literally incapable of injecting power back into the system.
The analysis applies relentless logical pressure on this point. From the grid's perspective, a load-equivalent solar system is electrically indistinguishable from, say, a massive commercial air conditioning unit. So why in the world does METI's regulation force these self-consumption systems to share the exact same strict cyber risk model as massive power-generating assets? If physical hardware prevents them from acting like generators, why regulate them as if they are generators? And that leads directly to a massive, logic-defying gap in the entire framework. If the policy is genuinely worried about sudden load changes destabilizing the grid, well, what about all the unregulated load-side equipment out there? Think about the thousands of networked EV chargers and EcoCute water heaters. They could easily be hacked to turn on or off all at once, causing massive disruption. Yet, they aren't subjected to the same strict control frameworks as a physically blocked solar panel. The source fiercely demands an explanation for this massive discrepancy.
Finally, let's explore Section 5, the LEAA alternative, which is essentially a survival strategy.
The researchers here don't just point out structural flaws. They actually present a cold, physics-based alternative known as LEAA, or the Load Equivalent Autonomous Resilience Architecture. This is a strategy that relies on physical, architectural reality rather than flawed certification schemes. Step 1 is a physical air gap, completely separating software control from physical protection relays. Step 2 is autonomous islanding, meaning the system disconnects locally during grid abnormalities without waiting for some cloud command. And Step 3 establishes true, undeniable load equivalence.
Take a look at the core principles of this architecture. The RPR hardware makes reverse power flow physically impossible. Full stop. The protection relays are physically separated from the IP networks. And perhaps most importantly, critical parameters can only be changed by a human physically turning a key on-site. The beauty of this is that even if the energy management software is hacked, or even if every single certified device is completely compromised by a nation-state actor, that physical protection layer simply cannot be overwritten by software.
So, as we wrap up this explainer on IS3's highly technical dissection of METI's framework, we're left with one incredibly cold, provocative question about the future of our grid. When dealing with massive systemic cyber threats, do we really want our critical infrastructure protected by a thin, static layer of bureaucratic paperwork? Or do we want it protected by the indisputable, unhackable laws of physics? Definitely something to think about next time you hear about securing the power grid. Thanks for joining me today, and keep questioning the systems around you.